Okay, so I'm glad to see everybody here. You should have a handout that should be at your table. It's just a supplemental packet. If at any time you need one, I'm just going to go ahead and maybe leave them in the back. All right, so we were in chapter 7. To jog your memory, I think it would be prudent to just do a brief history of the time that we discussed last time. So we'll start off, we left off starting to talk about the uncertainty principle. We'll go through the Schrodinger equation. We'll discuss quantum numbers, which is going to be new for you. Actually, the Schrodinger equation and the uncertainty principle are also new for you. And then one of my favorite topics, but maybe the most difficult topic to talk about, are nodes. Really weird term, but you'll see. Okay, so to get us up to the uncertainty principle, let's discuss what we went through Friday really quickly. We went through a slight history of the quantum model. In order to understand chapter 7, you really need to know the history of this development. Okay, so Planck said what? Do you remember? Let's reconnect the neurons. All right. I believe this in 5 days. Planck said light is quantized. Okay, next heavyweight in the quantum world came along. Einstein is just a heavyweight in general. What did Einstein say? What did he say about light? He said, let's call them photons. That's what he said. Okay. Okay, next guy up was Bohr. All right, what did Bohr say? He said that if light is quantized, and we're seeing these line spectra coming from the atoms, then what does that mean for the electrons? They too have quantized energies. So the electron energies are also quantized. So this chapter is really all about quantum theory. Right? So you hear the word quantized coming up a lot. Okay, and then after Bohr came Louis de Broglie. And what did he say? What might be an explanation as to why the electrons just don't fall in the nucleus and we have atoms collapsing in on themselves? So if light is quantized, and if electron energies are quantized, and if light behaves as a wave, that means, what does that mean for electrons? They also behave as a wave, right? So that's when I did my run around the room and lost my breath last time, and I kind of ran around as a wave, right? Okay, so electrons also behave as waves. What famous experiment confirmed the wave nature of electrons? We kind of left off talking about that last time. Yeah, the double slit experiment, right? And so what they did was they took 2 beams of electrons, or actually a beam of electrons, sent through 2 slits, and what they found was that they saw a diffraction pattern on the screen behind the 2 slits, reminiscent of constructive and destructive interference. Just like you would see if you sent a light source through 2 slits. You'd see that same pattern, right? So that confirmed that electrons also have wave characteristics. And then we also started to talk about Heisenberg. And what did he say? All right, there was an extra little part of the double slit experiment that they did. They took a laser beam and shot it across the two slits as the electrons are coming out of the slits. And what did they notice about the diffraction pattern after the laser beam was hitting those electrons? What did they notice about that? They noticed that the diffraction pattern, did it stay or did it disappear? I hear some whispers, it disappeared, right? So what that means is that we cannot observe the wave nature of electrons while at the same time trying to determine their position at the same time, right? So Heisenberg said, okay, we can't pinpoint the location of an electron while at the same time knowing its energy, right? That's what we're really getting at. Okay, so let's talk a little more about Heisenberg. Okay, so we introduced this equation. The uncertainty in a particle's position times its mass times its uncertainty in its velocity is greater than or equal to h over 4 pi. So when a photon strikes a particle to determine its position, its velocity changes. So let's do a sample problem of this. Okay, so an electron moving near an atomic nucleus has a speed of 6.2 to the 7th meters per second, plus or minus 1%. Okay, so that plus or minus 1%, that's the uncertainty in the velocity. Okay, or it's a percentage of the uncertainty. Can we be certain of the electron's location in a typical atom that is about 1 to the minus 10th meters in diameter? Okay, the mass of an electron is given as 9.11 times 10 to the minus 31 kilograms. Okay, that's kind of a mouthful. Let's just break down the equation. Now we can work with the uncertainty principle equation. We can assume that this is an equal sign just for the sake of working with it. All right, but you'll see. Okay, so h over 4 pi. So what is this problem asking us? It's saying, can we be certain of the electron's location? So what is it asking us to solve for in this equation? Is there a variable in here that represents the uncertainty of the location? Yeah, delta x, right? So we need to find delta x. That's what it's asking us. So let's solve for delta x. So delta x is equal to, greater than or equal to h over 4 pi. And it's also going to include in the denominator now m times delta v. So h is what? What does that represent? Planck's constant, right? And 4 pi is also a constant number. Do we have m? Do we have the mass of the particle? Yes. We do, right? So we really just need to find delta v. Okay, so what is delta v? All right, so looking at delta v now, it says that the speed is 6.2 to the 7th meters per second, plus or minus 1%. So if you took the 1% of something, what would that be? If you take 50% of something, what do you multiply it by? Like 50% is 0.5 of something, right? So what is 1%? 0.01, right? So we're just going to say 0.01, okay, of this velocity is going to represent the uncertainty in the velocity. that's going to give us 6.2 times 10 to the 5th meters per second. Any questions so far? Am I making any sense on this fine Friday morning? No? All right. So we're going to go ahead and plug this back into our equation above. All right, so delta x is equal to, or we can say greater than or equal to, so h is going to be 6.626 times 10 to the minus 34 joule. Yes, question?
How did you get the 6? Oh, never?
Yeah, this was given to us.
I
Yeah.
just saw it.
Yeah, it's given to us. Okay, that's okay. Keep asking. All right, so we divide Planck's constant by this 4 pi times n times delta v. So 4 times pi times the mass of the electron times this delta v. All right. Let's look at the units of this. Do joules have anything to cancel with here? Oh, yeah.
For all the problems like this, h is going to be the same number?
Yes, yeah. Planck's constant is just that, it's a constant. So the joules you can see have nothing to cancel with, and so same with the kilograms. Well, what units do we want from this? The uncertainty in a position, is time a unit of position? No, right? Is energy a unit of position? No. Is meters a unit of position? And the answer is yes, right? We think about position as a distance. So do you remember what conversion factor we can use to deal with the joules and the kilograms? Do you remember that? If not, you might remember this one. For every 1 joule, you have a kilogram meters squared per second squared. All right, so that again, we've been using that for a while. That comes in handy in a lot of calculations. So the joules will cancel. The seconds here will cancel one of these per second squared there. The other per second will cancel the bottom one. We also have kilograms to cancel, and then the meters squared will cancel out one of these meters. So we're going to be left with a unit in what unit? We'll have a unit of meters at the end of our calculation. So punching these numbers in, and of course, you all know how to divide by powers of 10 now. All right, don't forget to use your parentheses. So you get a number, and it's delta x is greater than or equal to, it should come out to be 9.3 times 10 to the minus 11th meters. So what does that mean for this problem? Can we be certain, so the question is asking us, can we be certain of the electron's location in a typical atom that is 1 to the minus 10th meters in diameter? Okay, so atom, here's the atom, it's a sphere. Okay, here's the diameter, and the diameter is around 1 to the minus 10th. Okay, so does this uncertainty in the location fit somewhere in this diameter? Can it fit? Is this number greater than or less than the diameter of the atom? Yeah, it's a little bit counterintuitive because you see a bigger number here, 11 versus 10. But remember, this is a negative exponent. So the higher this number is with a negative exponent, the smaller it is. So the smaller our uncertainty, that will indeed fit somewhere in this atom. Okay, so we can say, since delta x is less than the diameter of the atom, we can be certain that the electron occupies somewhere in that atom. In other words, yes, we can. Sounds like a campaign pitch. Yes, we can. Okay. So any questions about the uncertainty principle? It's kind of a weird equation, but making sense of it, you have to compare the uncertainty to the parameters it's giving you. So we said we have an atom that's about 10 to the minus 10 meters, and the uncertainty in the position of the electron was within those parameters. You might get a problem where the electron uncertainty and the location is actually larger than the atom, and then we can't say for certain it's going to occupy that atom. So we kind of work, when we work with this equation, you can see that we have a greater than or equal sign. We keep it there, but we kind of work with the equation as if it's an equal sign, not greater than. Okay, so I always like asking this question. Uncertainty principle, who cares? Okay, who cares about this stuff? Right? We're going through this really esoteric concept. Another form of the uncertainty principle, and this is not in your textbook, but I think it's important to paint some context for you. Okay, another form of it looks like this. Okay, so you have the uncertainty in the electron energy times the uncertainty in the time that an electron occupies a specific energy state. And again, it's greater than or equal to h over 4 pi. Okay, so what this means, you know, in real terms, I did research that sort of utilized this concept, which is why I get a little excited about it. In other words, if you tune your light source to a wavelength that a molecule absorbs at, to a strong absorption band of interest, you're making delta E small. Okay, you're making that uncertainty in the electron energy small by tuning your light source to a wavelength where the molecule absorbs. So it's just like when we were doing the Coolidge experiment, right? Why did we tune our wavelength to around 500 nanometers? Well, because red-40 dye doesn't absorb at other wavelengths that are far away from that. Okay. So by making our delta E small, we're making delta T big. Okay, you can't have both of these small at the same time. When one gets smaller, the other one gets bigger. Okay, so when you're making delta T large, you're increasing the lifetime that an electron spends in a given energy state. And I utilized an ionization method using lasers to where we were ionizing a molecule through an excited state. Okay, so just to not get into too much detail here, but if you wanted to analyze a mixture of compounds that was really complex, let's just say you have 100 compounds in a mixture and you only want to ionize and detect one compound in that mixture. How do you ionize something that's just that one compound and not the others? Because we don't want to analyze anything else, we just want to detect that one compound. So we went through an ionization process where we went through 2 steps. And so you tune your laser beam to a strong absorption band of interest for maybe the first group of compounds. So maybe out of those 100, maybe 10 of them still absorb the first photon. So you get to this excited state, and what you want is only your molecule to absorb that second photon to get to be an ionized state. Okay, so imagine these are shells in the Bohr model, just by analogy. So by making delta E small, you're now increasing the delta T, the lifetime that the electron resides in this second state. Okay, and then by using a second photon of a different wavelength, you ionize only that one photon of that mixture to this ionized state, and all the other molecules get left behind. Isn't that cool? So to make delta T small, make delta E small, make delta T big, and you increase the lifetime that that molecule spends in this excited state, and then you allow for a second photon to ionize that one molecule. Okay, so I did that in my research. We call that resonance-enhanced multi-photon ionization. But this is an application of the uncertainty principle. Right? Really hard to find real-world lab experiments directly related to this, but that's my experience with it. Okay. I've got a sample problem associated with it. We can go through it if there's time at the end. All right, so I'm just going to skip forward to by about 4 slides. So an alternative interpretation of the uncertainty principle based on this alternative that I gave you. It is impossible to know how long a particle will be in a specific location while at the same time knowing what its energy is going to be. And so the location and energy of small particles can be approximated by solving an equation for a wave. All right, so again, when we use a photon to hit that electron in that atom or molecule, its position changes. Okay, so it's kind of hard to figure out where the electron is while at the same time knowing its energy. So by approximating a wave equation, since we know electrons behave as waves, we can approximate the energies of electrons, or in other words, approximate the probability of finding an electron at a given distance from the nucleus by solving an equation for a wave. And this is where Schrodinger came in. So Edmund Schrodinger, a couple years after Heisenberg came out with his uncertainty principle, developed an equation to describe the wave nature of the electron. All right, but it can be viewed as taking into account the particle too, but mainly the wave nature of the electron. And it has a very simple form to it. The spread out, expanded form of the Schrodinger equation is really ugly. Okay, and you can look it up online if you want. It looks like mathematics hell. Okay. We're not going to actually do calculations with this equation. We're just going to talk about it. H is something called the Hamiltonian operator. If you take Calc 4, which if you really want to learn the math behind this, take Calc 4. I highly recommend it. It's my favorite math class I ever took. So H is the Hamiltonian operator. It's called the differential operator. The psi is called the wave function that describes the electron's wave nature. And E is the energy of the electron. And in differential equations, you learn something in math called eigenvalues and eigenvectors. And this is an eigenvalue eigenvector problem. And what they have is they have functions that will transform other equations into multiples of that same equation, and that multiple is the energy of the electron. So when you solve this equation, you're solving for a series of wave functions that give you a series of electron energies. Because let's face it, all atoms except for hydrogen have multiple electrons, so you want to know what the energies of all those electrons are. So the goal of this equation is to find E. All right, what is the electron energy? But as I like to ask, who cares about this stuff? Okay, who cares about electron energies? Well, so electron energies can be used to predict how molecules absorb light. And as you found in the Kool-Aid one, a lot of analyses are done through light absorption. Okay, so some compounds are highly unstable and make them difficult to detect. Kool-Aid and red 40 dye, it's just in your solution. It's not degrading in front of your eyes, right? It's stable. In my research, what I had to deal with was molecules that exist for microseconds at a time. How do you detect a molecule that exists for only microseconds at a time? Okay, and that means you have to know where to look to detect it before it disappears. Okay, and it's hard to scan wavelengths when a molecule is only existing for microseconds at a time. And so by doing calculations, by doing theoretical work, you can solve, in theory, for these electron energies and what wavelengths might be viable to look at to detect a compound like that. Okay, so the Schrodinger equation is useful, and there's been lots of other theories that have been developed since the Schrodinger equation that piggyback on that concept. But this is why we talk about electron energies and why the Schrodinger equation is so important. So for the Schrodinger equation to be solved, the wave functions themselves are a function of 4 numbers. Okay, we call those the quantum numbers. And those quantum numbers are n, l, m sub l, m sub s. Okay, and we'll go through each of those 4. The energies of the electron can only be solved, or the energies of electrons can only be solved or approximated for a specific set of quantum numbers. So the wave functions cannot be arrived at unless they meet the criteria of those 4 numbers. And those 4 numbers have rules to them that we will go through. The square of the wave function yields the probability of finding an electron in the nucleus. Right, so we'll go more into that. The probability of finding an electron in the nucleus can be placed out in 3D, and those volumes that the electrons occupy are called orbitals. So you know how you go like SP, D, and F orbitals? Do you remember those from Chem 107? Those actually represent solutions to the Schrodinger equation. All right, so just to tie it back to what you may have seen. Okay, so let's talk about quantum number n first. The rules for n is that the quantum number has to equal either 1, 2, 3, 4, up to infinity. All right, it has to take increments of 1. You cannot have n equals 0. You cannot have n equals 1.5. You cannot have n equals 2.3. It has to be exactly in whole number increments up to, it can go up to infinity. So what n represents is essentially how far is the electron, on average, away from the nucleus. So here's 1s, 2s, and 3s orbitals. You see these, n equals 1, 2, and 3. The orbital looks the same, it's just that as you go to higher energy levels, the orbital just gets bigger. Right? The line gets bigger. Okay, the next quantum number is the orbital shape quantum, or I'm sorry, it's called the angular momentum quantum number. We call that L. Okay, the rule for L is that it has to take on some value less than n. All right, so if you look at this, it says L must equal 0, 1, 2, 3, and it can only go up to n minus 1. A more simpler way of saying this is that L just must be less than n. Okay, it can't be the same. So if n is equal to 1, L has to can only be 0. If n equals 2, like for example with a 2s orbital, okay, L can be 0 or 1, but for a s orbital it's 0. We'll get into what these values represent more. If n equals 3, L can be 0, 1, or 2, but it cannot be 3. So I cannot have L equals 3 here because, again, L must be less than n. I know I'm not speaking English right now, so I'll get there. Okay. So the L value doesn't represent the size of the orbital, it represents the shape of the orbital. So if I were to tell you to look at one slide in your lecture notes, and you need to memorize this is it, okay? So the quantum number n tells you the size, the quantum number L tells you the shape. It tells you which orbital, which kind of orbital we're talking about. So if L is equal to 0, you have an s orbital, you have a sphere. Okay, if L is equal to 1, you've got a peanut-shaped orbital called a p orbital. P's for peanuts. L equals 2 gives you a d orbital. Okay, and L equals 3 gives you an f orbital. Okay, L equals 4 could be a g orbital, right, if you kept going. But we really are concerned only with SP, D, and F. So memorize this slide. We put a star next to it, say, I must memorize these values. Okay, because they tell you the shape of the orbital, they tell you what kind of orbital